Hello everybody. In this video we're going to prove limit as x is approaching to 0 of sine x over x equals to 1 using two different methods, squeeze theorem and table. And then we'll compute 5 important limits that all beginner calculus students should know. Limit as x is approaching to 0 of 1 minus cosine x over x. Limit as x is approaching to 0 of 1 minus cosine x over sine x. We're going to compute the same limit using different method. And then we'll move on to limit as x is approaching to 0 of x squared over 1 minus cosine x. And then we're going to finish with limit as x is approaching to 0 of 1 minus cosine x over sine of 2x. Please follow me with a piece of paper and pencil. Let's start by constructing a unit circle with center O, and let's make a tangent line to this circle. Let's make a tangency point here and a tangent line here. We know that tangent line touches the circle only at one point. And tangent line by definition is perpendicular to the radius. So here we can construct a right triangle. Let this triangle be triangle OAB. We know that the radius of a unit circle is 1. And this radius is also 1. Let the angle here be angle theta. And tangent theta by definition is equal to opposite over adjacent. Our opposite according to angle theta is line segment AB. And adjacent is line segment OA. And OA is 1 because this is a unit circle. So our tangent theta is equal to AB over 1, which is AB. So we can label line segment AB as our tangent theta. Now, let's compute the area of triangle OAB. The area of triangle OAB is given by 1/2 times base times height, which is 1/2 times our base is line segment OA, and our height is line segment AB. So it's going to be 1/2 times 1 times tangent theta. So from here, the area of triangle OAB is tangent theta over 2. Now let's consider the sector of OA. Let's call here C. The area of sector OAC, let me highlight it, this green area, will be given by the sector area formula. Sector area formula in radian is 1/2 times r squared theta. And here our radius is 1 because this is a unit circle, 1 squared, and we have theta. So the sector area, this green area, is theta over 2. Let's keep this in pocket, like this one above. Now let's consider this red triangle. Triangle OAC that I highlighted. The area of triangle OAC, let's use the alternative area formula. Area of triangle OAC. So the area of this triangle will be given by 1/2 the legs of the angle, which is side OC, side OA, sine theta. This is one of the alternative area formulas for triangle. So from here our OC is 1 because that's the radius. OA is also 1, that's the another radius. So it's going to be sine theta over 2. Now let's compare these three things. We know that the red triangle is less than the sector area OAC, and it is less than triangle OAB. Geometrically, if you check here, the green sector area is less than this triangle OAB, and red triangle is less than the sector area, the green area. Now let's set up the compound inequality. And we know that the green triangle OAC is less than or equal to sector area of OAC, because we have extra slice in here, and that is less than or equal to this big triangle OAB. The area of green triangle OAC is given by sine theta over 2. We found it. And the area of this sector is given by theta over 2. And the area of triangle OAB is given by tangent theta over 2. Now, using this compound inequality, we can multiply whole terms by 2 because the denominator is common. So we obtain sine theta is less than or equal to theta, that is less than or equal to tangent theta. Now let's divide everything by sine theta. So we obtain here 1 less than or equal to theta over sine theta. And we know that tangent is sine over cosine divided by sine theta here. So sine thetas cancel out, so cosine theta stays. So 1 less than or equal to theta over sine theta, less than or equal to cosine theta. If we flip the fraction, 1 over 1 is still 1, and inequality changes, sine theta over theta, and greater than 1 over cosine theta. Now we can take the limit on each side. Limit as x is approaching to 0, or theta is approaching to 0 in our case, of 1 is greater than or equal to limit as theta is approaching to 0 of sine theta over theta, greater than or equal to limit as theta is approaching to 0 of 1 over cosine theta. Now limit of the constant is the constant. Limit as theta is approaching to 0 of sine theta over theta. And here we can directly plug in. So 1 over cosine 0 is 1. So here cosine theta, we plug in 0, and cosine 0 is 1, so it's going to be 1 over 1. So by squeeze theorem, limit as theta is approaching to 0 of sine theta over theta is equal to 1. The opposite is also correct. Limit as theta is approaching to 0 of theta over sine theta is also 1. Now this is one of the important pocket limits that you will be using. So you need to memorize this. You don't need to derive it every time, just directly use it. Now we're going to use the second method, tabling method, and then we will use it in our computations. This time let's write an Excel formula for this. So from left, we would like to know what's the value of sine x over x as x value is getting closer and closer to 0 from the left, versus what's going to be the sine x over x value as our x value is approaching to 0 from the right. So we would like to pick up like tiny closer number to the 0 from the left. What that might be, negative 0.1. And next smaller step will be negative 0.01 and 0.001 and finally 0.001. Let's do from the right approach as well, the positive version of this. And let's write the formula in Excel and compare left and the right. Because the Excel sheet will give you the angle in radian form, so you don't have to worry about it. If you're writing table by hand, make sure your calculator is in the radian mode. So the formula we're going to write here will be, let's keep equal sign, which means we're writing a formula. Then built-in function sign, parentheses. In the parentheses, we're gonna copy this cell, close parentheses, divided by, again, this cell, and enter. So sine x over x of negative 0.1 is already 0.99. Now let's do one more step. Equal sign, sine of this cell, close parentheses, divided by this cell. Getting closer to the 1. And one more step, sine of this value, close parentheses, equal to sine of this value, close parentheses, divided by, again, this cell. It already converged on the third step, on the left. On the right, equal to sine of positive 0.1 divided by positive 0.1. Second step will give us sine of 0.01 divided by 0.01, and next step will be sine of 0.001 divided by 0.0001, already converged to 1 on the third step. So by table we can also see that left limit is equal to right limit on the third step. So we can conclude that limit as x is approaching to 0 of sine x over x is 1 by tabling method. Now we're going to use this as our template limits. Now let's get back to our limits that we're computing. Our first limit is limit as x is approaching to 0 of 1 minus cosine x over x. For this limit, we're going to utilize Pythagorean identity. Pythagorean identity for trigonometric functions, sine squared of x plus cosine squared of x is equal to 1. And from here, if we solve for sine squared of x, by subtracting cosine squared of x on both sides, we obtain 1 minus cosine squared of x, that is equal to sine squared of x. And as you can realize that 1 minus cosine squared of x is the difference of two squares. So we can rewrite this as 1 minus cosine x times 1 plus cosine x. That is equal to sine squared of x. So we can multiply this limit by 1 plus cosine x over 1 plus cosine x. 1 plus cosine x over 1 plus cosine x is 1, and if you multiply anything by 1, you don't change it. So we just rearrange this. So our new limit is these two fractions multiplied. On top, we obtain limit as x is approaching to 0 of 1 minus cosine squared of x. In the bottom we obtain x times 1 plus cosine x. And we know that by the Pythagorean identity, that is equal to sine squared of x. So limit as x is approaching to 0 of sine squared of x over x times 1 plus cosine x. Now here we have two factors of sine x times sine x. So let's separate it. So limit as x is approaching to 0 of sine x times sine x over x times 1 plus cosine x. Now we can separate the fractions because we have desired pocket limit, which is sine x over x, that we have proved at the beginning of the video. So we can rewrite this limit as x is approaching to 0 of sine x over x times sine x over 1 plus cosine x. And we know that from our template, as we have proven using this quiz theorem and table method, limit as x is approaching to 0 of this limit is 1. Similarly, limit as x is approaching to 0 of x over sine x is also 1. So this is 1. And here we have no restriction on the denominator, so we can directly plug in. So that's going to be sine of 0 over 1 plus cosine of 0. Sine of 0 is 0 and cosine of 0 is 1. So 0 divided by 2 is 0. So therefore, this limit as x is approaching to 0 of 1 minus cosine x over x is equal to 0. Now you can add this to your limit bank or limit templates. Limit as x is approaching to 0 of 1 minus cosine x over x is equal to 0. You don't need to derive again and again, so you can use these limits as your template. Now let's go to second limit we're computing. As we have seen in the previous limit, we have seen that sine squared of x plus cosine squared of x is equal to 1 using Pythagorean identity. And from here, sine squared of x is equal to 1 minus cosine squared of x. And we said that this is the difference of two squares. 1 minus cosine x, 1 plus cosine x. So we're going to multiply both top and bottom by 1 plus cosine x. So our limit as x is approaching to 0 will turn into 1 minus cosine squared of x over sine x times 1 plus cosine x. And we can replace 1 minus cosine squared of x with sine squared of x. So our limit as x is approaching to 0 will be sine squared of x divided by sine x times 1 plus cosine x. Here, one factor of sine x cancels sine x and leaves with limit as x is approaching to 0 of sine x over 1 plus cosine x. Now we have no restriction on the denominator, so we can directly plug in. Sine of 0, 1 plus cosine of 0. Here it's going to be 0 divided by 1 plus cosine of 0 is 1, so this limit is equal to 0. Therefore, limit as x is approaching to 0 of 1 minus cosine x over sine x is equal to 0. Let's get back to number 3. On the third limit, we have same limit as number 2. This time we're going to multiply both numerator and denominator by x. So we're going to multiply this limit by x over x. And then we can rearrange the limit as x is approaching to 0 of, let's do these two, x over sine x times 1 minus cosine x over x. We know that from our template limits this is equal to 1, and we have proven this on number 1 that is equal to 0. So 1 times 0 will be 0. For this limit we're going to utilize half angle identity. Let's remember what half angle identity was. Half angle identity for cosine squared of x over 2, which is the half of the angle, is equal to 1/2 1 plus cosine x. And for sine x, sine squared of x over 2, we have 1/2 1 minus cosine of x. So whatever the angle here, we double it here. For cosine we use plus, and for sine we use minus. So utilizing the half angle identity, we can replace 1 minus cosine x, 1/2, just multiply two sides by 2. If you multiply everything by 2 here, you obtain 2 sine squared of x over 2 is equal to 1 minus cosine x. So 1 minus cosine x can be replaced with 2 sine squared of x over 2 using the half angle identity. So our limit as x is approaching to 0 will turn into x squared over 2 sine squared of x over 2. And then we can multiply both numerator and denominator by x over 2 squared. And we can separate into two limits. This one and that one. So we have limit as x is approaching to 0 of x squared over 2 times x over 2 the quantity squared over sine squared of x over 2 times 1 over x over 2 the quantity squared. Using the laws of limit, we can rearrange this one. They are both in the squared form, so we can also separate the limits. Or let's keep this one for now, but rearrange the middle part. X over 2 divided by sine of x over 2 the quantity squared. And this is going to be 1 over x squared over 4. And 1 over x squared over 4 is equal to 4 over x squared. Let's rewrite this as 4 over x squared. We know that this limit is going to, it's like x over sine x. As x is approaching to 0 of this limit, we know that this is one of our template limits is 1. So that's going to be 1 squared, and here x squared cancels x squared, so this limit is 4 over 2, which is 2. Now you can try limit as x is approaching to 0 of 1 minus cosine x over x squared and 1 minus cosine cube of x over x squared. Let's go ahead and do our fifth and the last limit. Our last limit requires double angle identity. Double angle identity for sine of 2x is equal to 2 sine x cosine x. So we can replace sine of 2x as 2 sine x cosine x using double angle identity. So our limit as x is approaching to 0 of 1 minus cosine x over 2 sine x cosine x will be our new limit. Now, as we did in the previous limits, we're going to multiply both numerator and the denominator by the conjugate of 1 minus cosine x. So we can utilize difference of two squares. So limit as x is approaching to 0, 1 minus cosine x times 1 plus cosine x is equal to 1 minus cosine squared of x. Using Pythagorean identity, 1 minus cosine squared of x is equal to sine squared of x. So we can replace that with sine squared of x. So our numerator will be 1 minus cosine squared of x. Our denominator is the same. And using the Pythagorean identity, 1 minus cosine squared of x will turn into sine squared of x. We have 2 sine x cosine x in the bottom. One factor of sine cancels this sign, leaving this. So our limit will turn into sine x over 2 times cosine x. Now we have no restriction on the denominator, so we can directly plug in 0. 2 times cosine of 0. Sine of 0 is 0 and cosine 0 is 1. So it's going to be 2 over 0. It's going to be 0 over 2. So limit as x is approaching to 0 of 1 minus cosine x over sine of 2x is equal to 0 using double angle identity. I hope you enjoyed these 5 important limits. Practice them and then use them as a template. Thank you for watching.